Okay, so today we're going to continue using integrals to do stuff. And the first thing we're going to talk about is calculating volumes by cross-section. I have a question. What's the volume for a sphere of radius r? A pluses for this man. You may leave. I've already given you an A plus in my mind. Writing it down. Volume of a sphere of radius r. 4/3 pi cubed. Right, the exponent has to match the unit. So it's meters cubed. Yeah, 4/3 pi r cubed. But the question is why is it 4/3 pi r cubed? And we're going to develop the equation for the volume of a sphere and a bunch of other typical volumes. But we're going to start with this one. So here's our motivation. What is the volume of the, you probably have never heard of this shape, equilateral square base pyramid? So this is one that has height, capital H, and square base, h by h. Okay? So that would be this. Can you imagine this shape? You hold it in your hand. It's a pyramid with a square base. And if you measure any of the sides, they're exactly the same. That's what makes it an equilateral square-based pyramid. Right? The fact that this h is the same as the height. Oh, no, sorry. It's not all the sides are the same. It's the height. The height of this pyramid is the same as the base of the pyramid. So what's this length here? This is an h by h square. I'm just trying to test your 3D comprehension. So if this is h by h, what's the diagonal? Square root h. Okay. Okay, so the idea is that we want to estimate the volume of this. And we've already been talking about estimating areas. So it's not a very big jump to now do a volume instead. So we took an area and we cut it up into square rectangles because we knew how to take the area of the rectangle. For a volume, we can easily break up the volume into a bunch of prisms. Right? This is just the natural one dimension up about what we were doing. So do you believe that if I cut this pyramid into three pieces like this, well, I'm not really cutting it. I'm approximating it by this shape. So do you believe that this is sort of approximately this guy? Okay. And do you believe that we can calculate the volume of this? Right. Okay. So what do we need to calculate the volume of one of these prisms? Yes?
Base height length.
Base height length. Okay, so the first one here is going to be the bottom. So we know that that's h, and that's h. If there's three of them, this is going to be delta h, which in this case is, delta height, in which case is going to be h over 3. Right? So each of these is going to be a delta h, change in height. And for each of these prisms, the volume is going to be h squared by delta h. Okay. So we want to form how do I write this as a sum now? What do I need? So like this prism is h by delta h. How do I get the volume of this prism? Well, just tell me what I need to get the volume of this prism.
The height same as the base?
Yeah, the height's the same as the base, so I got the height. So what do I need?
Isn't it just h over 3 by h over 3?
Well, don't we need these sides?
Yeah, which is the same as the height.
This height is delta h. So this is not, it's not going to be, these aren't cubes.
Okay.
These are prisms.
Okay.
If it was a cube, you'd be right. But I'm not trying to draw cubes. For one, this h is going to be a lot big. Like this can't be a cube. This side length is h and its height is h over 3. So what do we need? So we need to know what the side lengths are at some height. Right? Specifically, I need to know what the base of this square is at height h over 3. So how can we figure that out? Well, okay, so you have to This is why I want you to look at me today, right? Because we're going to have to like rotate shapes, 3D shapes in our brains. So I want you to look at this pyramid. So imagine it. So you have one of the edges looking straight at you. And what I'm going to do is I'm going to cut it from the tip here with a knife through the center, through the diagonal of the base. Everyone with me? Okay. So if I do that, we are going to get a picture that looks like this. I'm going to draw you the face of the pyramid. And I'm going to draw it upside down just because it makes the math a little bit easier. But if I calculate the volume of the upside down pyramid, it's the same thing as the upright pyramid. Okay, so if we cut the pyramid along its diagonal and look at it, you're going to get something that looks like this. Okay. This was the diagonal, so that's going to be delta H. The height, right, so we're going to make this axis height. H. So if I go here, that length is delta H. If I go here, let's just take a height sample. We need to figure out what that length is. So it turns out for these equilateral square-based pyramids that this length is going to be square root of the height sample. Right? So if we go up a little bit, that's the diagonal. Oh, that's the whole width here is given by that. So given this picture, this means that if we look at the slice at height h star, or height sample, the diagonal here is given by square root that, which means that the side lengths here are given by that. Isn't that what you said? Oh, no, you said delta H. This is a different H. Okay, so this is a fairly well-structured pyramid. This is why I chose it. I chose it because it has this real nice property. Otherwise, the math will get over necessarily complicated. Okay, so now I know that the area of a slice at height h is equal to that, h squared, right? So if I take this pyramid and I slice it, you're going to have a face like this, or this, or this, and each of these areas are given by that area equation up there. Agree? Okay. Okay, so what do we need to do now? So let's try to write a sum for this volume, right, that I've drawn here. So we're going to have to add up how many things? 3 things, right? Okay, so we're going to have to add up 3 things. Let's call this the first one, the second one, the third one. Or I guess we have to call this the first one, this the second one, this the third one, since we flipped the triangle, right? Because our h direction is this way. Okay. So what do I have to do? I have to go k equals 1 to 3, volume of the prism at the sample, right? This is it informally writing the sum. Does that make sense? Right, I have to go here and I have to go to the base of this and say what's the volume of this prism. Then I have to go to the base of this and ask what's the volume of this prism, and then that one. So what's the volume of a prism? You told me before that it's length times width times height. Right? The length times width here is just the area at the height sample. Right, so we're going to get sum k equals 1 to 3 of the volume of the prism, which is going to be at height h at the sample. It's going to be h k, that's the length, that's the width, and this is the height. Agree? Usually silence indicates weak understanding.
What's the x in
this case? Oh, you're correct. Sorry. Should be delta H. Yeah, good. All right. Delta H, sorry. Yeah. Because we're moving along the height. I'm just trying to show you that we can change the labels and use the same techniques. All right, but then I guess I should change the labels properly. Okay, I really don't want to delete my fuss drum. Can you remember this equation? It's just sum k equals 1 to 3 of hk squared, delta h. Okay. Okay, so how can we do the same experiment now for n many prisms? Right, so the volume is going to be approximated by, let's now do n many prisms. That means I have to do, well, it's the length at k, the width at height k, times delta h, where what is delta h now? Right, if I have to divide the height into n pieces, how big are each of these heights? Huh?
1 over n.
Well, it's h, where it's the pyramid is h high.
H over n.
H over n, yeah, so it's close enough, right? Actually, it's very typical in math to say just divide it through by h. Make it a unit height. It makes everything easier. Height over n. Okay, so we got this, which is equal to k equal 1 to n of h, that sample squared, delta h. But what happens if we take the limit of n goes to infinity of this? Like the natural thing we want to do is approximate the volume by pushing the number of prisms to infinity. So we're going to get this. So then what is this equal to?
Zero?
Hmm?
Like if n goes to infinity, wouldn't it be zero?
What would?
Because delta h is h over n, and if n is going to 0, then it would be just times 0, right?
You never complained about this when I was doing this with areas. It never actually gets to 0. It limits to 0, right?
Okay.
This is the most critical thing about the integral. Doesn't this look like something?
Oh, do we find the antiderivative of this?
Not yet. What integral is this? Like this is what the whole fundamental theorem of calculus was for, right? Taking this geometric thing and making it something algebraic. No?
Okay. Now what?
Well, now we're finished, right? Because we can do. Okay, I'm going to do this over and over and over today. Again and again and again. It's the only thing we're going to do. So please ask me questions about this. You got to stare at it. We got to understand it. Yeah.
I don't understand the connection. How do we get that? Like,
Well, this is basically like the area under the curve.
okay.
And we've determined that was the integral. There's this theorem you have which says this is that integral.
How does it we know that it goes from 0 to h?
Oh, because delta h is h minus 0 over n. This is a Riemann sum, right? Does that help?
Yeah.
Yeah, this is a Riemann sum, right?
Okay.
I just did it along h instead of x, just to show you that the labels don't really matter. Right? Does that help? If I say this is the Riemann sum for the volume?
Wait,
Yeah.
Over there, with the sigma notation starts at 1, but when we changed it to the other notation, we started at 0.
Because it's the age.
Well, because I have the first prism, the second prism, the third prism. Like, there's no endpoints here.
K is
Right.
the amount of epsilons you're splitting it. H is not.
Well, you didn't complain when I did it with 3. Right? This is for 3. That was for n.
We didn't write it in integral.
So if you would change
I can't write this as an integral. That's a sum. That's 1, 2, 3 things. I don't need an integral for that. If the number up here is finite, you don't need an integral. The integral comes into play when where's the other? The integral comes into play when you need to take this to infinity. Right? Okay, suffice it to say, the limit of a Riemann sum gives you the integral. That's like super important. That's what we've been developing over the last few days. Like, so this association, okay, we're going to try it 4 more times, and then maybe by the end of class you'll get it. But the point is the limit of a Riemann sum is the integral. Right? We spent a lot of time trying to develop theorems for that. Okay, so the answer to this question is h cubed third. Right? That's the volume of this prism. Okay, so let's try another one. And then maybe that'll clarify things more. Well, okay, maybe I could explain it like this. So if you really wanted to take this n to infinity, as you pointed out, this becomes 0. So how do we then add up an infinite amount of stuff when I don't know how to walk through the interval? I'll try to explain something. This may make sense or it may make things worse, but let's try. I told you that we could write a sum like this, right? X over some set, right? X. You can do this, provided that X is something countable. Like I sort of made that implicit. Like you have to be able to list the numbers of X. Okay? Here's something that we're not supposed to write. What is this? What is the sum of all the numbers between 0 and 1 on the real line? Well, that's not possible. The last thing is 1. And then I'm definitely going through a half, right?
Okay.
So it's more than 1 plus 1/2. Okay, so the first number is 0, yeah? What's the next number?
Infinite numbers.
What's the next number after 0 on the real interval? You pick anything, I'm going to go halfway. So do you understand that, like, the real numbers, you can't order them? You can't, like, they don't have the property of being countable. Like, there are different types of infinity, right? 0, 1, 2, 3, 4, 5 to infinity is an infinite collection of integers, but I can count them. I can order them, right? This is allowed to be a set of integers. This cannot be something over the reals. Like, this doesn't make sense as a sum, right? It's saying, okay, the first thing is 0, the next thing is, okay? So we need some way of running this sum, right? Of running a sum of x over every number in this interval somehow. And how do we do that? Right? That's what the integral is doing. It's taking a sum, this is deliberately an S, a sum of these quantities for every h between 0 and h. Right? This is like saying, I'm putting quotes because it's definitely illegal. The sum for every h, yeah, the math police will come and get me. For every h in the real interval 0 to h, and I want to add h squared delta h. Okay? This sum doesn't make sense if you can't do it, right? Because this thing is not ordered. So the recourse for this is this, right? So we said, okay, we can do it with finitely many points, but we can push that limit to infinity so we can have an infinite many points. And when we do that, we end up getting the integral. Right? This is very, very, very important, that this integral is a sum, and it's a sum where you're sort of taking your index over a real interval. Does that help a bit? Yeah. You're nodding, but you always nod. I appreciate it.
So the big H can be less than 1.
You're going to have to think about it, right? This is complicated. It's calculus. Okay, so think about that. I'm going to write down the boards.
Integration is like the boundaries of this how many are inside.
When in reality, I what I
So that will yeah, when you were like get what it's like how many are but then when you write the integral, it's like between that like it's
Okay.
So wait, Professor, would this be like FTC 1?
Huh?
Would this be FTC part 1? Like what part of the theory is this related?
Well, it's the fundamental theorem of calculus, period. We established a connection between the geometric limit of a Riemann sum and what the integral is. Like, that's why the fundamental theorem of calculus is so important.
Okay, and then
Okay, so here's another rule for you guys, or I'm just going to give you a definition. You better pay attention because it's going to be on your midterm. Secret words. I'm not even being facetious, right? So on your midterm, you're going to have to do a bunch of these, right? We're going to ask you to take the volume of shapes by cross-section. We're going to ask you to take the volume by revolution. We're going to ask you to take the arc length. We're going to ask you to take the surface area, right? So this is an important lecture, and I'm not able to do it as slowly as I used to. Okay, so we're going to continue doing volumes. I'm just going to give you a general statement. Okay. So definition. The volume of a solid whose cross-section at x in the interval AB is given by A, x, is, and you're going to tell me what it is. I'm going to make you a little drawing. So this is sort of the setup. You're working on the axis like this. You sort of take your shape, like imagine your 3D shape, take it in your hands, and skewer it along that axis like it's a kebab or what are they called here? Skewer. Yeah. Like something you put on the barbecue. Right, so take your shape, skewer it along there, and what's going to happen? So, I don't know, you got some sort of like shape that's going around here. It may be sort of like a vase or something like that. Who knows? The point is, it's a squash, sure. The point is, between A and B, so between A and B, that you have some type of equation, AX, which is reporting the area of this. Right? So you take your object, you just skewer it, and then you make slices perpendicular to the y-axis, and you get a surface area. Oh, sorry, you get just an area of, well, I guess it's just an area of that slice.
and then you add up the area.
And then you add up the areas, right? But like we have to multiply them by an infinitely small volume, right, to make it a volume, and then run that limit. So then, okay, so provided you have this area, right? So like basically what you're doing is you're going to have this disk, and then maybe you're going to add that disk, and then the next disk is bigger. It's just to say it's a Riemann sum with disks instead of rectangles. So what is the integral that will give me the volume of that shape?
The area of a circle approaching infinity. Do we just add up the areas?
Yep, how do we do that? Walk the x-axis from A to B, and for each point on that interval, sum AX. That's how you can interpret the integral, right? And when you do this, right, again, we have to see this as the limit of a Riemann sum. You're going to end up getting the volume of this shape. All right? We're going to do another one. We're going to deduce the volume of a sphere. Okay. Okay, so volumes by rotation. Okay, so one way of giving this area is to say that we're going to be given a curve, just a curve f. Right? So this is the normal way of being given a curve, just as a function. Okay. Okay, so here's what you have to imagine. That like I've cut out a piece of paper, right? So this area is occupied, occupado. And what I'm going to do is rotate this around the axis. That's what this symbol means. So can you imagine what happens if you take like a sheet of paper or something and rotate it? Right? I want you to imagine that this is going to sweep around And what we've swept is going to be the volume. Right? So if we rotate this, you're going to get something that sort of looks like, again, this squash-like structure. Right? It's going to look something like that, a volume. So I guess I should add some depth. Where's all my things? All right, we're going to have stuff that looks like that. All right. So it's a closed volume. Right, so provided, if we know, it's like the special thing about these volumes of rotation is that this AX here is always going to be given by what?
The area of your cross section?
The area of
Your cross section.
yeah, of my cross. Well, in this case, it's the circle, though.
Yeah.
So specifically, the area in this case, right, is just going to be. So this is going to form a radius, right, at x. So the radius at x is going to just be pi f of x squared, pi r squared. Right. So if we're asking you to rotate something, there's a very natural area to choose. All right. So let's do an easy one first, and then we'll do the sphere. So here's an example. What shape do you get if I give you this line, y equals c, and what did I put in the notes? R. Okay, and I go from A to B. What shape do you get when you rotate this? Cylinder. In fact, that's also called a cylinder. Anything which you can cut and produce a circle every time you cut is a cylinder. Cylinders are basically created by these rotations around the axis. Okay, so does anyone know the equation for the volume of a cylinder?
1/3 pi r squared h.
Okay, so the volume of a cylinder, you said is 1/3.
No, that's a cone. That's a cone.
That's a cone.
Not height.
That's not like, should be
What
just
is it?
2 pi, no, pi r squared times the height, no?
Pi r squared h.
Okay, so it should be pi
Pi r squared h.
r squared h, but in this case our h is what?
A to b.
B, well, yeah, b minus a. Okay, so we can deduce that, but now let's confirm this like with integrals. So what integral, this is a valid midterm question. Right? We may ask you to set something up and then not resolve it, right? Because integrating and setting up integrals I see as two different skill sets. What integral gives me this volume? What did I say? Yeah. Oh, sorry, go ahead.
B to b of pi r squared.
Which r? This r, yeah? Right, so this r is a constant. It's not moving. Right, so this is a good example. How do I integrate this?
Isn't it just
We talked about this yesterday when I said, what happens when I integrate a constant?
you just added up that many times from A to B.
You're thinking of the summand. This is the integral.
You take it out of the integral.
Huh?
You take it out of the integral?
Okay, but then what? Then you have to integrate, yeah?
There's just one.
But the one
The r to the power of 3.
Oh god.
No, you're integrating with respect to r. This is a very, very simple Okay,
R squared and r squared.
You just take that out.
what's that?
X.
X.
Um,
Okay, so I can put whatever nonsense I want in there, and as long as it's independent of x, I get the same thing. So this is going to be pi r squared x from A to B.
Do
Okay.
you like switch it though? Do you put B on the bottom and A at the top? It's like,
No, that's the notation.
like on WebWork they would switch it, so. if-
Really?
Yeah.
That's non-standard notation, then,
Okay.
right?
It's like the B was on the bottom.
That doesn't make any sense. Every textbook I've ever looked at. Send me those Weeby works. Actually, I'll change them.
Okay, I
Yeah.
saw it somewhere.
Okay, so this is just going to be what? Pi r squared b minus a. There you go. So that's how you derive the equation for a cylinder. Savvy? Okay. How can we now derive the equation for the sphere, volume of a sphere? What do we have to spin around the curve? Well, I'm sweeping out like a sheet, and that gives me a cylinder. So what? Half circle. Which half?
Which half?
Yeah. Can I erase this?
Does it matter?
Yeah?
Does it matter which half of the circle? I'm not being facetious.
Oh, yeah, this,
It's a good word. It's
it's
the
like
only
this,
word
right?
in English language to tell
Volume of cylinder.
the same word.
What do I have to spin around the curve to get a sphere?
One other question.
Yeah. Semicircle. This? Yeah? Okay, or is it this one?
Oh, no, this one across the y-axis?
You want this one?
No, the other one across the
You want
y-axis.
this one?
I mean, both of them work.
Both of them will work. That's the point. You can take this guy and you can rotate it around the y-axis.
Oh, true.
Okay? Please, guys, if I teach you a method along x, I don't also have to teach you the method along y. Right? This is a skill set that you need. You need to be able to reorient the problem. Right? So there's going to be some problems today which I'll do along y, but don't get cranky with me because I never told you how to do it with y. Just put y into the equations. Or like just rotate your graph. Right? This is a skill that you need. You need to be able to relabel. Okay, so we can either do this guy and rotate like that, or we can do this guy and rotate like this. So I'm going to simplify it a bit further. I'm going to take just that and spin it, and that's going to give me half the volume of the sphere, and then we can just double it, right? Because this is going to let me go from what did I say the volume of the sphere was in the notes? The volume of the sphere was A. Okay. So we're going to find the volume of a cylinder of radius A. So what is the equation for this shape? Or name the shape. Or name the shape that this is part of.
Of a circle.
Thank Christ. Okay. So this guy here is x squared plus y squared is equal to a squared. Yeah? If I only want this equation for the first quadrant, right, then we can assume that x and y are both positive, which means I can do the following rewrite. So you're going to get y is equal to a squared minus x squared square root. And it's the positive version of this. It's always the positive version because we redefine the square root to like get rid of that ambiguity. Okay, so what integral do I need?
From 0 to a.
Okay, so remember, we need to take cross sections of the sphere, and those cross sections are going to look like this, right? Like eventually, like basically, I'm doing this. Right? But infinitely many of them that are infinitely skinny. So what integral should I be doing now? It's very simple, right? You walk along the curve and you just sum up the areas of the circles.
Oh, is it from negative a to a?
No, because I restricted it to the first quadrant and we agreed ahead of time that I'm going to double it. Yeah.
And it's not 0 to A?
It is 0 to A.
Okay.
Yeah. Okay, so we'll start there, 0 to A.
And then we write that at dx.
Okay, then what is the integrand? The thing. Okay, well, what axis am I walking across? What are these A's? 0 to. Okay, so we're walking along x. That means you're sampling x from 0 to a infinitely many times. Right? So what do I want to sum?
The square root.
Areas of the disks. Yes. So how do I get an area of a disk?
Pi times y equation squared.
Yeah, so this curve here is this y. So all I need to know is what this radius is at x. Agree? Okay, so but the radius at x is just given by a squared minus x squared. And that's what the curve is telling us. Okay, so I need to take integral of pi radius at x squared. Right? Disagree with me if it's not making sense. It's only going to get harder from here. This is the easiest one we're doing. Okay. So this means I need to take pi, the integral from 0 to a. Remember, this is equal to half the volume. Let's keep that in mind. We're going to have to square that. So we're going to get a squared minus x squared dx. If we integrate this, we're going to get pi. So give me the integral. With respect to x. Should be immediate.
A cubed divided by 3 minus.
No. No. X.
Minus x to the 3.
A squared x minus x cubed third. That worries me. That should be instant. I'm not trying to make guys make you feel bad. I'm trying to fire you up. Because I won't even finish my integrals today. We don't have time. I don't have time to go through and finish everything anymore. So please go home and do it. Okay, so we have a squared x minus x cubed thirds. If I evaluate this, just notice that the bottom summand is going to give me 0, right? Because there's going to be a 0 in both places. So it's going to be equal to pi a squared a minus a cubed third minus 0. This is 1a cubed minus a third a cubed, so this is 2 pi a cubed third, which is half the volume, which means that the full volume is 4/3 pi a cubed. So now you know why the volume of the sphere is 4/3 pi r cubed. Yeah?
Okay. Why did you do the y equals square root a squared minus x squared?
I need this curve. The whole curve, the whole thing is the circle. The circle restricted to the first quadrant is this. We played this trick millions of times in this class, right? Just to like work with parts of the circle. Because the circle isn't a function. I can't integrate over this.
And you said that equals the radius, because however much it changes, that would be the radius of the sphere.
Well, we agreed at the very beginning of this problem that if I spin a disk, it's going to sweep out a volume of a sphere. Yes?
Since we use the quarter of it, why are we still multiplying it by pi? Wouldn't it be like pi over 2? Because
I don't understand what the quarter has to do with the pi.
like the area is pi r squared, so basically it's the area of a circle, right?
Yeah.
So then since we're using half the circle, wouldn't we go pi r squared over 2?
I don't understand. If I sweep this out, you're going to get half the sphere. I know this is a quarter of the circle, but this is going to go 360 degrees. You're going to sweep out half the sphere here.
I think she's mixing up half a sphere with half a circle. Like, it's half a sphere, but still for full circles in that half of the sphere. So that's why you're not having your pi r squared.
Like the pi comes from the fact that we're spinning something. Right? I'm not adding pi to anything, right? Because pi comes from this, me saying we've spun, so the area of this, like the area of the sweep is a circle. That's where pi comes from the rotation. Right? Yeah. That's how we get a circle. Okay, so how was that? Yeah? But again, like we're just taking problems and we're like cutting them into an infinite collection of infinitely skinny pieces and then using an integral to sum them. Right? That's one of the uses of these integrals. What time is it? 11:58. Oh God. Okay, you take that in. I'll wipe down the boards.
Because a cubed minus a cubed over 3, I'm left with 2 here. Because I know a cubed.
Okay, so lots of practice is required for this. So here's your first piece of practice. There's an exercise for you. Find the volume obtained by rotating xy equal to over y in 1 to 4 about y-axis, x-axis. And the shape looks something like this. So you're going to go from y equals 4, y equals 1. The shape itself looks something like this. Okay? So I want you to do a rotation about here. I want you to do a rotation about here. You should get two curves. The first one sort of looks like this. All right, not the frustum, something different. And the other one looks something like this. Whoops. Okay, so do you see how I'm going to get each surface depending on which way I rotate? Yes. Oh, okay. Yes.
On a midterm, would you provide us pictures, or do we have to like, draw them out? Or, like,
You should be able to draw this. This is just 1 over x and 1 over y, right?
But I mean, would you like put something more complicated?
How would the picture help you? You're still going to have to integrate.
Sure.
Right? Well, like if like how would this help? Like you know that you're going to have to form a radius by going to the curve. It's funny because I emphasize so much how you guys should be visualizing something, knowing full well when you go higher level math, it's impossible to visualize anything. Right? We're very lucky to be working on the plane and like at most in 3 dimensions. I can't draw you a hypercube. I can't draw you a 4-dimensional cube. So at that point, you just got to trust the equations. Okay, so do that one. We're going to move on to the next thing. I really hope we can finish today, and we may not. What do you mean, what's 4-dimensional? All right, spinning boundaries. Okay, I'll just address your question, right?
No.
First dimension. That's the second dimension. This is a point in the third dimension. Right? You can just keep going, right? I don't know, height, like length, width, height, time. Right? And animated, like a moving shape is technically a fourth dimensional object. You're cheating at looking at it. You're sort of projecting it into the third. Anyway, screw this. I don't even know why I'm talking this. Right. Okay. So how do we do this now? Okay, so it's a little variation on the spinning thing, but it doesn't require that much explanation. Yesterday we were talking about taking 2 curves. And bounding the area. Okay, so notice as soon as I bound this area with 2 curves, right, I'm free to then spin it. Can anyone tell me what the cross sections here look like? You can just think of this as taking like the bigger cylinder and removing the inner cylinder. But there's another way of looking at this. Not quite. A donut is like a 3D thing, right? It is. It's torus. It's 3D. It's not quite. It's the flat version of that.
Sure.
Okay, so I'm just gonna.
It's a Lego donut.
Well, Lego's still 3D.
Whatever, man.
It's called an Analyst.
Are we not rotating this?
It's a disc with a disc removed. Right? So it's this, yeah? That shape is called an Analyst. And the analyst has two radiuses, what I'm going to call the inner radius and the outer radius. How do you get the area that this occupies? Don't overthink.
Whole thing minus the inner.
Yeah, the whole disk, right? So the area of the analyst is equal to the area of the outer circle minus the area of the inner circle, which actually is just going to end up being this. Okay? So given two curves, the area that they sweep in rotation is going to be equal to this. The volume swept by a bounded area of F and G is given by the integral from A to B of the area of the cuts, which in this case are going to be analy. So we're going to go from A to B. We're going to add up the areas of the analy along X. So this is going to give you the volume. Okay, so it's just a little twist about what we were doing beforehand. Now, you got to be careful with how you construct the inner and outer radius. And here's what I recommend. Pick which direction you're going to walk along. Right? So in this case, I'm walking along X, because it's the same axis that you're rotating along. Then you take your pencil and you strike a line perpendicular to the axis you're spinning around. The first thing you hit, if you follow this line from the axis, the first thing you hit, inner radius. Second thing you hit, outer radius. Right? And this may seem, why am I telling you this? Damn it. I wish these boards were self-cleaning. Okay, because, as you know, we could ask you to bound other regions in space. Okay, so I could easily ask you to rotate this around that axis and rotate this around that axis. Okay, so let's play the game again. So if I want to rotate around this axis, I strike my line. This is the inner radius. Up to here is the outer radius. Okay? If I want to instead rotate around this axis, I strike a line. It's perpendicular to y. Here is the inner radius, and here is the outer radius. Okay? Also, we can ask you to rotate these shapes about arbitrary axes. Right? So I can put this up. Right? In this case, you'd run to here, and you're spinning like this, in which case the inner and outer radiuses are given here. So you got to be a little bit more careful. You'll flesh this out in practice. But you can do it at the origin, you can do it at a shift. Okay, so I gave you, there's an exercise in the notes here. I'll write it. I'm not going to write the whole thing. Look in the notes for the full thing. So y equals x squared plus 1, and y equals 3 minus x. I don't want to hear any questions about Piazza about how this is undefined because it's in the notes. Okay, here are two curves. They will form a bounded region. So spin the bounded region about x-axis and y-axis and find volume. Oh boy. Oh boy. Okay, two more topics still. What time do we have?
12:10.
It's even hard for me. This is tiring me out, right? Keeping all this stuff straight. Arc length. This was one of your worksheet problems that I was trying to have you discover. So the idea is here is if I give you a function, a curve, and you take a piece of rope and you lay the rope along the curve, how long will the rope be? It's a good way of conceptualizing the arc length. Before we start that, there's one definition that I want to give you, and that's the definition of something called a chord. Just make things a lot easier if we can talk about chords today. So a chord, so given a function, so given a curve, a chord is a line segment portion connecting 2 points on the curve. Right, so for an example, right, here are 2 points. There's some curve that goes through them. I don't care what the curve is. I just care that the points are given by some curve. So this is going to be point x1, f of x1. This is going to be the point x naught, f of x naught. These are just arbitrarily chosen labels. And this is the chord. This is chord. Is everyone okay with that? Because I'm just going to say chord. And a chord is just a line segment that connects 2 points on a plot. All right. Why am I telling you this? Well, so we've been taking all the things that we want to compute and breaking them into smaller pieces. So if I give you a curve like this, over A to B. Well, we don't know how to measure the length of this. That's what we're trying to do. But what do we know how to measure the length of? We know how to measure the length of a chord. Like measuring the straight distance between 2 points is the easiest thing we can measure the distance between. Is it possible to break this thing up into chords?
Yes.
Yes. Okay, so I'm going to use the language that made you angry on the last quiz. Something funny happened. The other section couldn't solve the first part of the quiz. Because I gave you quite a strong hint that you should do the worksheet. They didn't get that strong hint. So it's funny, everyone did the opposite sides of the sheet.
Well, their part was worth more, no?
No, it was equal. 10 and 10.
Oh, okay.
Yeah. Okay. Because maybe this word partition confused everyone, and I sort of regret it, but it all sort of worked out in the wash. So like what we're doing when we're sampling is the first step of doing these Riemann sums is to break up this region between A and B, right?
Yes.
Yes, need at least one person to agree. So if I take this region down here, how many things did I break it up to in the notes? 5, I think. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. This is called a partition. We've partitioned A to B. Right? Actually, I looked it up. You do have I gave you the definition of partition like week 1. Like I know that was a long.
One?
Yeah. Partition is something that you should have known from high school. Taking a set and breaking it into disjoint sets.
He's
Yeah, but we
lowering-
didn't
he's
connect
lowering
it with
us, guys.
endpoints, that's why.
But you do have the definition of
He's
partition,
lowering- He's lowering us.
right?
I gave you it.
But anyways, so this constitutes a partition along A to B. So let's number these points. x1, x2, x3, x4. Let's call B x5. Let's call A x6. Okay, so over each partition, we're going to need an estimate for the length of this curve. So over this partition, I'm going to say this is an estimate. Over this partition, I'm going to say this is an estimate, this is an estimate, this is an estimate, and this is an estimate. Okay? Let's call this the first chord, the second chord, the third chord, the fourth chord, and the fifth chord. While I wipe the other board, I want you to write down the sum using the summed notation that will sum the length of these chords from 1 to 5 with the sigma notation.
What's the length of the line? X1, X1. A is X6. I mean, I suppose it's arbitrary.
Oh, so just give the curve a name. Call it F. You're going to need it.
That's not, I mean, that makes more sense to me. To be totally honest.
Okay. Let's just look at one of the chords. Let's look at C3. So C3 is going to be what? The chord that's connecting. It's going to connect what 2 points? X2, F of X2, and X3, F of X3. Now, we can give some sort of clever labels here to make everything a lot easier to write. All right. So we have a change in X for the third chord, and we have a change in Y for the third chord. So the change in Y for the third chord is this minus this. The change in X is that minus that. So given that, what is the length of this? Oh, I think I called that S segment. What is the length of the third chord? I've given you some labels now. Yeah. Just Pythagoras, right? It's going to be the square root of the sum of squares. Agree? Okay. But remember, we have a curve going through here. F. It's a chord. That's why I insisted on using this terminology, because the fact that we have a function is important. What does this setup look like? Well, remember the mean value theorem?
No.
You better, right?
No.
Suppressed memory.
Just keep nodding.
We need it. Anyone remember the mean value theorem?
Yes.
What is it?
There's going to be a point C over there where the derivative of it equals 0.
Exactly, he has it. There's going to be some point between here and here so that this tangent is parallel to that chord. Okay, so what does that mean? It means that by the mean value theorem, there is some number. I'm going to call it the third sample, and you'll see why, right? In between x2 and x3, right, on that picture, such that f prime of x, which is equal to change in y over change of x, is equal to, oh, sorry, I wrote that wrong. Where's my thing? I should write that all over again. There is a sample in this thing such that the derivative at that sample is equal to that slope, which is change in y3 over change in x3. Everyone, this is just mean value theorem, right? If this is a function and this is a chord, there has to be a point from here to here such that there's a tangent line that's parallel to there, right? Provided that the function is differentiable over this interval, which ends up being important. Any questions about that? Okay, so you agree that I can get this.
Yeah.
Okay, but from this I can deduce that the change in y3 is equal to f prime of this sample delta x3, right?
Yes.
Okay, that means I can simplify this guy to be delta x3 squared plus f prime x3 this squared times delta x3 squared, all of that's square root. Okay, please pay attention. There's a square root here. There's an x squared. If I factor that out, you end up getting 1 plus f prime x3 times delta x3 without its square. This like really irritated my class last year. I can't figure out why. Do you get this?
What is G first?
All right. I think I should just do the extra step. This is going to be delta x3 squared 1 plus f prime.
Oh, okay.
All right. Okay.
Okay.
Yeah.
You missed the half last time.
Wait,
Like you missed to the power half last time.
Well, no, because I'm going to take this power of a half and... Oh, did I make... Anyways.
That f prime is squared.
Yeah, that f prime is squared. 1 plus f prime x3 squared to the half delta x. Okay, that makes sense, maybe. If I dropped it half, sorry. Okay, that's important. Okay, good. You're still sort of with me. Okay, so we're going to play the same game, except we're going to break everything into n pieces now. All right, so here's our curve. We're going from A to B. Here's our first x. Here's the last one. Let's say we want to use n plus 1 many edges. So let's just look at the kth one here. Did I have to go backwards or forwards? I had to go backwards. Okay, so here's going to be the kth chord. This is the chord K. And we just found out that the length of this guy, the length of that chord, is going to be given to us, okay, by, so the length of CK, which we're going to call LK, is equal to, what did we discover up there? It's going to be equal to 1 plus f prime at this sample delta x half. Yeah? I'm just doing what we did at 3 at like an arbitrary point. But the funny thing is that this sample point is chosen by mean value theorem. It's like theoretically sampled for us, but that's actually no problem, and I'll show you why.
Is that still squared? The xk star?
Oh yes, sorry, this is the peril of recopying things, and this is why I'm begging you not to copy from the board, because it's the least accurate. My handwritten notes are barely accurate. Okay, so we have this as the length of that line, so can you give me the Riemann sum that's going to add up the chords?
Yeah, SK
Yeah, I want the first chord to the nth chord. I want the length of that chord, but the length of the chord is 1 plus f prime xk this squared a half delta x with delta x equal to b minus a over n. Everyone keeps asking, well, where is the boundaries hidden in these Riemann sums? It's here. It's hidden in your delta x. You can always recover the boundaries from delta x. Okay, but what happens then if I run n to infinity here?
Then we do the integral.
Yeah, but we have to worry about this thing,
Well, the point is.
right? Because this has been a point that's been sampled sampled by mean value theorem. But look at this. As I increase n, this integral is going to get infinitely tiny. So the point chosen by mean value theorem, we know what it has to choose. On an interval of length exactly 1, on an interval with exactly 1 point in it, it has to choose xk. And this is going to become, like, all of these 3 points are going to collapse on top of one another. All right, so this is actually equal to, and this is a semi-important theoretical step, but you don't have to understand it too much. That I can just, in the limit, that I can swap this out. That I can remove that sample and just give it the edge. It's a semi-important theoretical thing, but you don't really have to understand. Can you please give me the integral now that takes this? Well, every time we've done this, we've taken these boundaries, this has been the integrand, and this has changed to a dx. Right, so that's what this means, right? When we go from, notice as we take n to infinity, that delta x goes to 0. Right? The more edges, the smaller this gets, and that's exactly what this dx means. Dx means delta x, but the delta is tiny, arbitrarily small. Right? So we're going to take the integral from a to b of 1 plus, and I'm going to write it like this, dy dx squared a half. This is the arc length for y. We're not going to ask you to develop these equations. We're going to ask you to use them. Right? But you need to understand why the equations are the way they are in order to use them. Right? So if you're not understanding some of this development, it's okay, even though there's nothing really that should prevent you from understanding this. It's just utilizing the calculus that you've been learning to solve some real-world problems, at least real-world problems of
We don't
math.
have to develop the whole thing from the beginning.
No, you'll have to go to this equation and use it. You'll essentially have to do pattern matching. I am going to ask you to take the arc length for sure on your test. But essentially these are all, I just want you to understand, the most important thing to understand here is that an integral is something that helps us do a particular type of infinite sum. An infinite sum over an uncountable collection of infinite objects. What time do we got? 12:28. Okay, I gave you a problem. There's an arc length calculation in the handwritten notes. You can just look it up. Right? This will be very easy to use. Right? You just take any curve you want. You can take its arc length. So. Okay, hold on. Maybe we'll do one example, but I won't finish it because I feel kind of bad. I just want to show you that ultimately this will be simple. But when people ask me, like, how do you do math? Like, this is how you do math. You use old tools to try to, like, find values of other things. Because, like, using the mean value theorem here was a very clever idea. My math teachers in school would call that a magic step, right? A step that I would never think to do that. But, that's why some mathematicians get paid the big bills. Okay. Okay, so let's just do one example. I'll show you that's not too hard. what is arc length of y equal x half 2/3 for x in 0 to 2. Okay, well, I don't have time to lead you through this problem. But one of the things that you're going to discover here is that this is not integrable at 0 along x, right? So you have some type, this is a shape that looks like that. And if you tried to use the arc length formula to find the arc length of this, you would fail. If you were walking along x, right? You can take the derivative of this and see that it has no derivative at 0. However, this does have a derivative along this axis. And so that is to say, dy dx at x equals 0 does not exist, but dx at dy at y equals 0 does. Okay, because implicit to what we've been doing here is the assumption that the function that we were taking chords over was differentiable. So just be mindful of that condition. So I'll just show you that it's not too bad. We want to walk along here. So this point, what did I say? 0 to 2. So 2 is going to be at 1 here. So we have 2, 1. How high do we get? So 1. So if we're walking along y, we have to go from 0 to 1. This curve here is given by y equals x half 2/3, which means that x is equal to 2y 3/2, which means that dx by dy is 3y to the half. Okay, so I'm just going to use the arc length formula. So the arc length formula, we're going to walk from 0 to 1 along y, and we're going to add up the square root of 1 plus dx over dy squared, which in this case is going to be integral 0 to 1, 1 plus 3y half squared half dy. Okay, and you can continue from here. The answer I got was 2/27, 10 root 10 minus 1. One more. I know it's a heavy lecture today. You're going to have to go back and think a bit. Can I erase this? Okay. Okay, so we've done volumes, we've done arc length. What's left? What other properties of shapes are there? Surface area. Yeah.
Of revolution.
Well, surface area, period, right? It's something we got to talk about. Yeah. Okay. So we're going to restrict restrict ourselves to rotating stuff the same way that we were rotating to establish volumes, because the generalization of surface area may be a little bit hard. In any case, let's start. You may not have realized when we were doing volumes, we were actually approximating the volumes by like infinitely thin cylinders. We're going to start with cylinders again because we know how to take the surface area of a cylinder. All right, so if I have a cylinder, and it looks like this, this is an open face now. How do I denote that? I don't know. It's open, not closed. There should be a way. In any case, this is a cylinder. Let's say that it has height h. This is height h. And this has radius r. What is the surface area of this cylinder? Well, how can we determine the surface area? Yeah.
Did you unwrap it?
Okay, so let's unwrap it. So let's cut it. So we're going to cut it along here. All right, so it's like I've taken a piece of paper and I've done this. We're going to cut it along its height, and we're going to unroll it. So when we unroll it, what do we get? So here it is unrolled. There's the cut I made. Maybe I'll put that up. Like, there's the cut. So that means that this is h. How long is this?
Circumference.
Yeah, it's the circumference. So what's the circumference?
2 pi r.
2 pi r, right? All right, so the area of the cylinder is what? The surface area of this cylinder is what?
2 pi r.
2 pi r. Okay, so we can take the surface area and like just keep in mind that like we can get this cylinder by rotating that line about the axis. Yeah.
Shouldn't it be 2 pi r h?
Yep. Thank you.
No.
Not there.
No.
The
Surface area of a cylinder.
Oh yeah. Sorry, I'm going down. Okay. I'm trying. Okay. It's shitty because this is the toughest one. Okay. Okay. So for straight lines we can do it, but what about for chords? Right. So if I instead have a chord like this, and I rotate that along here, what kind of shape am I going to generate? I heard it. Rah! That. Frustum. Frustum. Not frustrum. Frustum. Right?
There is one. Beginning.
All right, so let's label a few things here. Let's call this the... I want to use the same labels. Okay, we're going to call this, so we're spinning, right? So this is the smaller radius. And this is going to be the larger radius. So let's try to figure out things here. Oh, and let's just label this. So I'm going to argue a little bit differently. Instead of using xk and stuff, I'm just going to say x. And we'll call this delta x. Does everyone get the setup? And there's some type of f. And there's a function f that's like really going through these 2 points. X, this is just a position along the x-axis, and I want to move out a little bit further. Everyone get the setup? Okay. So if I spin that around the axis, you're going to get something that looks like this. Agree? Like the skewer is coming out through the middle here. What I want to do is the same type of cut. I just have to be careful about where I'm cutting this. So I believe if we make a cut here, okay, and we unroll this thing and lay it flat, we're going to get a shape that looks like this. Agree? Okay, so now we have to figure out the dimensions of this thing. So we have some type of, we have like a circumference here. Let's call that the circumference at 0. We have like a bigger circumference out here. This is the circumference at 1. So what is this distance? according to that picture. Oh, I think we may not be able to do that quite yet. Okay, let's do that last. Can you get me the circumference? So like, here is a circumference, which is going to end up being this distance, yeah? So tell me what this circumference is. Well, it has radius r naught.
2 pi r naught.
2 pi r naught. What about this one?
2 pi r1.
2 pi r1.
Just kind of draw it reverse.
Okay, so let's start labeling this guy. This is going to be 2 pi r1. Oh, no. This is the smaller one, 2 pi r naught. And this length here is going to be 2 pi r1. Okay. So we still need to get this dimension. So let's work it out. So remember that we're working on a chord, right? These 2 points lie on the curve f, right? Right. So this point in particular, this one was x f of x. And that point up there was x plus delta x, f x plus delta x. Right, so if we just make these labels again, if we just say, so we have delta x, and we just need a delta y. Right, so delta x is just delta x, and delta y is going to be f at x plus delta x minus f of x. That's the height. This is going to be given by delta x squared plus delta y squared square root. Just the chord. I'm just taking the length the same way that I did last time. Okay, let's go back to this picture up here and try to notice some things. Can I express r1 in terms of r naught? So just remove that curve and let's draw in some extra pieces. Okay, so what's this distance? R naught. What's this distance?
R1 minus R naught.
Well, I'm going to say delta y. That's what we just established, right? So we know that R1 is equal to R naught plus delta y. But we also know in this case, so if this is delta y and this is delta x, and this thing is a line, what is delta y over delta x? What is the relationship between f prime and x and delta y over delta x?
Derivative slope
What symbol should I put in here?
equal.
Equal. This is the definition. It's a line, right? So if I take, there's a function here, its derivative should give me that tangent, right? So it's going to be exactly equal to that. So this means that I can write this as delta y can be written as delta x f prime of x. So this guy is actually equal to r naught plus delta x f prime of x. Last one, it's the last one. Okay, so here's where we're going to wrap this all up, right? Because what are we going to do? Okay, so I know that R1 is R naught. Was it plus? Yeah, plus delta x f prime x. And we know that when we take n to infinity, all right, because the idea is we're going to break this into n many frustums. What happens to delta x if we take n to infinity?
It approaches 0.
Goes to 0. So what does that mean about R1 when we're like taking delta x to be small?
Equal R naught.
Yeah, so limit as delta x goes to 0 of R1, which is equal to the limit as n goes to infinity of R1 is equal to R naught. Yeah? Well, what does that mean about this shape when I make delta x tiny?
It means that the two sides are gonna be equal.
The top thing and the bottom thing become the same width in the limit.
But it approaches the smaller one.
Huh?
It like goes to the smaller one. It doesn't go to the middle, right?
Well, this is just becoming infinitely narrow.
Yeah.
And in that limit, it looks like a rectangle. I don't know how to take the area of this. I do know how to take the area of a rectangle. I don't, yeah, area of a rectangle.
Oh, you're saying it goes.
Yeah, it becomes infinitely narrow in the limit. And at that, when it's infinitely narrow, its curvature is negligible. It actually looks like a rectangle. This is what calculus is for. It makes curved things look straight when you look at them very closely. And we know how to work with straight objects, right? I prefer to take the area of this rather than the area of this. Curves are hard. The integrals are used for curves. Okay, so all we need now then is this length, which is, we're going to play the same game. So I know that I have delta x squared plus that of that. We worked that out before. So this is going to be 1 plus dy dx squared half delta x. Okay? So I've got to wrap this all up now. All right, so when, well, yeah, I'm sorry. You're going to have to study this, right? When delta x is small, we know that the surface area of the cylinder is equal to the surface area of the frustum. Read the notes. I only was able to do 2 of the 4 pages that were there. Okay, because look, if I want to take the surface area by rotating this guy, right, what am I going to do instead? Well, my approximation is going to look like this. I'm going to rotate the chords instead. This is going to generate two frustums. And then I add the surface area of the frustums, and I assume that that constitutes an approximation for the actual surface area. And as I use an infinite number of frustums, you'll get the exact surface area. So what I have to do now is say, I want to, the surface area is going to be equal to, I should have given it a label here. You want to walk along the x-axis from A to B, taking infinitely small steps. And at each step, I want to add the surface area of the frustum. And the surface area of the frustum is given by this. Oh, 2 pi. Okay, so this is the equation for the surface area of a object given by a curve that's rotated around the y-axis. Now again, I'm not going to ask you to develop any of these things. I know it's complicated. But what I am going to expect you to do is to be able to utilize these equations. We're going to give them to you. We're going to ask you questions. They're going to be plug and play. These are great type of questions for the fill in the blank, right? Because you just need to do pattern matching. Right? I may ask you, give me the integral that gives me the following arc length. Give me the integral that gives me the following surface area.
We wouldn't be given the shape, so we'd have to be able to picture it from the function you give us.
Well, why do you need to picture this in order to do it? Like, what about this do you need to
wouldn't know
picture?
if it's this, really. It could be in,
What?
like, I don't know if it's the frust, it's an M line.
You don't need it anymore. It's gone. This is I brought in the frustum to justify this
So
equation.
this is the surface area for any,
Give an f, spin it around the axis, x in this case, from A to B,
yeah.
and this equation is going to give you the surface area. And I just explained why, right?
Even if it's like decreasing, not increasing.
Oh, because you said the curvature wouldn't matter, that's why. It would be like rectangle.
Yeah, because the frustums that we are going to add are going to be formed over infinitely small intervals, in which case those frustums look like cylinders. And I know how to take the surface area of a cylinder. It's like the first thing that we did by unrolling it. We've done this over and over and over again. Right? We're saying, I don't know how to take the volume of this curve. I do know how to take the volume of like that, right? So if I cut my object into these sort of like disks, then I can add up those disks. I don't even know what this is called. It's a disk with a little bit of volume. And then for the arc length, we broke it up into chords and added those chords together. And for this one, we just chose the frusta. In each case, we chose an object to slice, and then we use calculus to like make it infinitely small and add it. This used to be 4 lectures. Like I know that this was a tough lecture. Like I don't expect you to understand everything. Again, first contact. The handwritten notes that have been scanned and are on Piazza already are a little bit more robust than this, and there's a ton of examples that you can look at. But what you need to take from this lecture, if you don't really understand anything, that's fine, but be sure to be able to use equations like this. So Piazza is a great place to start. But you do have the ability to understand everything I said, if you reflect on it a bit. I didn't use any powerful mathematics that we haven't already seen. All right. Have a good one.